Good morning, gentlefolk. So today we are going to learn some tricks to make partial fraction decomposition just a little bit less unpleasant. I'm going to show you these tricks through examples, and then we'll have a bit of a discussion about when they are most useful, when they are not useful. And we'll work a few problems that we haven't worked yet. So far, the only PFD problems we've done are problems in which all of the factors of the denominator are simple, non-repeated linear factors. I think we did one case with a repeated linear factor, and that took some time, right, at the end of class on Friday of last week. So before we get started, this is, of course, Calc 2. Section 002. It is a lecture, and today is the 28th. I'm sorry if you hear that noise. My computer's fan is definitely screaming while it finishes processing the video from my last class. It should just be a few more seconds now. So today we're going to do more PFD. Specifically, I'm going to teach you something called the Heaviside trick. Which is also sometimes called the cover-up method. And we'll do some examples from homework. The study guide for exam 1 is up. I'm sorry I did not get it up on Friday. We had a fairly busy weekend up here, but I finished it yesterday, got it up yesterday morning, so you can work on that at your leisure. The exam, remember, exam 1, which is going to cover all the integration methods, so U sub, all the way through partial fractions, including like trig sub, trig integrals, all the stuff that we've learned, integration by parts. That's going to be on October 5th, which is 1 week from today. You may have noticed I posted an announcement to Canvas. Oh, sorry. You may have noticed I posted an announcement to Canvas giving instructions for study guide 1. Please read this whole thing. All right, it's important. I'll post a similar announcement explaining exactly what you need to do for exam 1, so the procedure and all of that. Please get some practice scanning using Cam Scanner or the Notes app, whatever you're going to use. And make sure that you can submit things to Canvas. So I don't believe there's a way to scan and then directly submit from Cam Scanner. So if you're using Cam Scanner, you're going to have to scan, save the PDF as a file on your phone in a folder to which you have access, and then upload that file to Canvas. So you can't go straight from Cam Scanner to Canvas. You have to save the PDF either on your phone or on your laptop, and then upload to Canvas. You want to do that as soon as you can. Get the study guide in as soon as you can. That way I can annotate it with some feedback like I would on the test. And that way you're not seeing how I give feedback and how I critique problems for the first time on the test. There's a little note in here, don't cheat on the study guide. I don't want to see what Symbolab or Bartleby or any of those bullshit things have to say about these problems. I know what they have to say about these problems. I want to see what you have to say about these problems. That way I can give you feedback that will be useful to you on the test. If you just copy down what Symbolab, Bartleby, whatever has, then the feedback I give you isn't going to be in any way useful for the test. I don't grade the study guide for correctness. I just grade it for completeness. So if you've gone in there and solved those problems to the best of your ability, you will get 25 out of 25 on the study guide, regardless of whether your solution is correct or not. I want to see what you do. That way I can help you do better on the test. There is no reason at all to cheat on this study guide. So please don't copy it, don't Google it, don't anything it. Just do the problems. That means you need to take the time, but it's a super low pressure environment. All right, so let's take a look at these tricks for partial fractions. They will save you a lot of time. The first guy, let's grab from the homework. Normally I would let you pick the problems, but we'll do that on Wednesday. Today I'm going to pick the problems. That way I can kind of cultivate the example environment a little bit. So we're going to start with number 14 from homework 5. Here we want to integrate y over 5y minus 1 times y plus 2 dy. The integrand here is a rational function. It is a ratio of two polynomials. Is this a proper rational function, or do I need to long divide first?
Is it proper?
It is proper. Why is it proper?
Because the denominator has a higher degree.
Very good, right? Remember, a proper rational function is one in which the degree of the numerator is strictly less than the degree of the denominator. Here, the degree of the numerator is 1. The degree of the denominator is 2, because if I multiplied this out, I would have a y squared. So this is a proper rational function, which means I don't need to do any long division, so I can jump straight into my PFD setup. The PFD setup says my function can be expanded as a sum of simpler rational functions, a over 5y minus 1 plus b over y plus 2. And this is coming from the PFD Bible that I showed you guys last week. Because both of the factors there are simple, non-repeated linear factors, each term, each factor contributes one term to the partial fraction setup. This is the nicest of all possible cases. The next move, just like we were doing last week, is to clear all the denominators. So I'm going to multiply through by 5y minus 1 times y plus 2. Over here, when I multiply by 5y minus 1 times y plus 2, both cancel, and you just get y. When I multiply this by 5y minus 1 times y plus 2, the 5y minus 1's cancel, and I get a times y plus 2. And the second term on the right-hand side, when I multiply this by 5y minus 1 times y plus 2, the y plus 2's cancel, and I get b times 5y minus 1. This is the equation that we were calling star last week. So I'll continue to call it star here. Heaviside was a man. That was his name, Heaviside. I believe he was German, but I'm not sure. The Heaviside trick comes from an observation. Heaviside observed that this expression, star, is more than an equation, it's an identity. So vocab time, does anybody remember the difference between an equation and an identity? Like sine squared x plus cos squared x equals 1, that's an identity. What's the difference between an identity and an equation? equations have solutions. Not every number solves an equation, right? Like x squared equals 5 has 2 solutions, just 2. It's plus minus the square root of 5. An identity is true for every value of the variable. Meaning star is true for any y value we can plug in. So Heaviside's observation becomes useful when you realize I can plug shit in for y here and still get a true statement. Why is that so useful? Well, because imagine I plug in -2 for y. Okay, this would be a -2. Oh, this would be 0, because -2 plus 2 is 0. And this would be b times some number. Then I would get -2 equals some number times b. Shit, I can solve that for b immediately. So I get to skip that whole process of setting up a linear system and row reducing. You can skip all of that.
So on the test, if we were to like follow or solve a type of equation similar to this, will we be expected to solve it like a specific way, or can we solve it?
You can do it however you want.
Okay.
Now there will be some instances where the Heaviside trick gives you everything, and there will be some instances where the Heaviside trick doesn't give you everything. And today, one of my goals is to help you understand which situations lead to which outcomes. But you can always try this. So if I plug in -2 for y, something really nice happens. The equation star, the identity star, becomes -2 equals a times 0 plus b times, -2 times 5 is -10 minus 1 is -11. And the miracle of doing this is that the a's go away. So I get -2 equals -11b, which implies that b is 2/11. That's the Heaviside trick. So you plug numbers into the equation or identity star, which make as much as possible go away, leaving hopefully just one of the coefficients and some numbers like we got here. That will allow you to solve for the coefficient. How do you pick the numbers to plug in? You ask, well, what makes this factor 0? This factor is 0 when y is -2, so I choose to plug in -2. Does that make sense? If I plug in 1/5 for y, something nice will happen also. Then the identity star becomes 1/5 equals a times 1/5 plus 2. 1/5 plus 2 is 1/5 plus 10/5, that's 11/5, plus b times 5 times 1/5 is 1, 1 minus 1 is 0. So I chose 1/5 because I knew it would make that 0. In other words, I have 11/5, or 1/5 equals 11/5 times a. And if you multiply both sides by 5/11, you'll get a equals 1/11. No linear systems, no row reducing, no elimination, no equating coefficients. All the stuff that makes PFD difficult is avoided by this Heaviside trick. So take a second, make sure your notes are clear, and then let's take any questions on what it is that we did here. Any questions on these two maneuvers? I plugged 1/5 in for y, and then I just did the arithmetic. So 1/5 plus 2 is 1/5 plus 10 over 5 is 11 over 5. That's all.
Can I see this, like the side of the paper where the identity portion's written? Oh, thank you.
So we've discovered that A is 1 over 11, and B is 2 over 11. So now I can come back and do my integral. This means that the integral of y over 5y minus 1 times y plus 2 dy is equal to the integral of this stuff with those values plugged in. So that's 1 over 11 divided by 5y minus 1 plus 2 over 11 divided by y plus 2 dy, like this. And now from here, I'll split up my integral, pop out my constants. I get 1/11 times the integral of dy over 5y minus 1 plus 2 over 11 times the integral of dy over y plus 2. And each of these requires a little u sub. In the first, I'll make the substitution z equals 5y minus 1. So dz is 5 dy. And then we should use a different variable, w maybe equals y plus 2. And in there, dw is just dy. Under those substitutions, this integral, this 5 will give me a 1/5. When I combine the 1/5 with the 1/11th, I'll get 1 over 55 integral dz over z plus, here at my 2/11ths just comes along for the ride, integral dw over w, both of which are natural logs. In the first, I'll have the natural log of the absolute value of z, and in the second, I'll have the natural log of the absolute value of w, and at this stage I should write my plus c because I no longer have any integral symbols. Finally, we go back to the original variable. And we're done. Isn't that so much nicer? So I think the integration here is stuff that everybody's probably super comfy with. What I want to make sure you're comfy with is this procedure. So I'll push this up and zoom out a little. Any questions on the partial fractions, the algebra that we did at the start? It's nice, right? Now, unfortunately, the Heaviside trick, as glorious as it is, will not always give you all the coefficients so fast. If your PFD setup is that simplest possible case where all the factors of the denominator are simple, non-repeated linear factors, then Heaviside will allow you to recover all the coefficients. So what I'd like to do now is address the other possibilities, that you have a repeated factor downstairs or an irreducible quadratic factor downstairs. I'll leave this here for just one more second. Are there any questions at all on this problem? Okay then. Hey Bubba, how you doing, handsome? So let me see what I have in here for you guys. I don't want to rob you of your experience with this. Let's do number 16, because here we do have a repeated factor downstairs. So I don't anticipate that Heaviside will do everything for us, but I'll show you how it can still help us quite a bit. So that's the integral from 0 to 4, x squared plus x plus 1 over x plus 1 squared times x plus 2.
Is that number 16 or 17?
Did I write the wrong problem number down? It is, it's 16, sorry. Okay. So again, I do have a proper rational function. The degree of the top is 2. The degree of the bottom is 3, because if I multiplied all this out, I would have an x cubed. So I don't need to do any long division. I can jump straight to my PFD setup. You have to remember that PFD Bible I gave you guys last time in order to get the setup correct. I have to ask, what possible things could have contributed to either of these factors being in the downstairs? The x plus 1, because he is squared, could have come from something like this, or also could have come from a combination of something like that with a something like this. So the x plus 1 quantity squared contributes these two terms to the PFD setup, and then the x plus 2 contributes just this. Is everybody comfy with that?
Why is the x plus 1 squared underneath the b?
So remember from your PFD Bible, if you have something like, where do I have some scratch space? If I have something like x minus r to the m, then that will contribute m terms, something like a1 over x minus r plus a2 over x minus r squared. We have to build all the way up to whatever the power is that we have downstairs. So if you have like x minus 1 to the 3, you would have a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. If I had like x plus 1 to the 7, there would be 7 terms in my PFD setup coming from that factor. So because I have an x plus 1 squared, I need to have 2 terms just coming from him. Because if you combine 2 things like this with a common denominator, you'll get this factor downstairs. So anytime we have a repeated linear factor, we have to give terms that build all the way up to that power in our PFD setup. Because a factor like this in the original doesn't necessarily just come from something like this, it could come from adding up 2 things like these. So both of these terms are coming from this guy. I'm glad you're asking about that. That is a common mistake I see, is people not including both of those terms. Are you comfortable with why they're both there?
Yes.
From here, our next step looks the same as it always does. We cross multiply to get rid of all the denominators. So when I multiply by x plus 1 squared times x plus 2, everything cancels on the left and I just get the numerator. When I multiply this by x plus 1 squared times x plus 2, one of the x plus 1's will cancel, one of them won't. So I'll have x plus 1 times x plus 2. When I multiply this by x plus 1 squared times x plus 2, both of the x plus 1's will cancel, and I'll just get b times x plus 2. And when I multiply this by x plus 1 squared times x plus 2, the x plus 2 will cancel, and I'll get c times x plus 1 squared. So that's what we have after clearing the denominators. And at this stage, I can invoke Heaviside. It's always nice to let your reader know what you're doing. So before I write my PFD setup, I write PFD. That way whoever's reading my work can tell what I'm doing. Before I use the Heaviside trick, I write Heaviside, so my reader again can tell what I'm doing. Remember what the Heaviside trick is. We're going to take this expression here, star, and I'm going to plug things in for x that make stuff go away. So the nice numbers to plug in here are the numbers that make these factors 0. One of those numbers is -1. So when x is -1, star becomes -1 squared plus -1 plus 1. That's 1. -1 squared is 1, minus 1 is 0, plus 1 is 1. So this is 1 equals, when I plug -1 in here, I'll have a times 0 times 1 plus b times -1 plus 2 is 1 plus c times -1 plus 1 is 0. This is just the statement 1 equals b, right? That 0 times a and 0 times c. So boom, immediately I get the value of B out. Extremely clever and extremely fast. There is another number I can plug in here to make a bunch of stuff vanish, and that's what makes this factor 0. That's -2. So my next move in the Heaviside trick is to plug in x equals -2. Because when you do that, the equation star becomes -2 squared is 4, plus -2 is +2, plus 1 is 3. And then on the right-hand side here, I'll have a times -2 plus 1 is -1 times 0, plus b times -2 plus 2 is 0, plus c times -2 plus 1 is -1, and then squared. So again, these guys both go away. And -1 squared is 1. So you just get 3 equals c. So immediately we get the value of c as well. If you go looking through this now for a number you could plug in to get the constant a, you'll find that there isn't a number that will make this and this 0 without making this 0 at the same time. This is the downside of this square. So the fact that we're not in that nicest possible case, the fact that we're in the case where we've got a repeated factor, tells me that Heaviside won't give me everything. Heaviside gave me 2 of the 3, but not the 3rd. What we do in this instance is we update the equation star with the information we have. So now, we can update star with the values of b and c, with b equals 1 and c equals 3 to get, well, so this side will still be x squared plus x plus 1. Over here, I'll have a times x plus 1 times x plus 2 plus b is 1. So b times x plus 2 is just x plus 2. C is 3. So c times x plus 1 squared is 3 times x plus 1 squared. And I call this 2 star. So all of my Heaviside work is here. That's the end of the Heaviside trick. But now I have this 2 star identity. And it only has one unknown that I'm still trying to solve for. One option at this point would be to multiply everything out, gather up coefficients, and set up a system. But because there's only one unknown left, that's more work than is required. Remember, this is still an identity. This is still true for every number x in the universe. You can plug whatever the hell you want in. And while there isn't a number I can plug in that will allow me to read a off directly from here, once I've got the values of b and c plugged in, if you plug in any other number besides -1 or -2, like 0, 1, 5, 7, pi, any other number, you'll get an equation that just has a and numbers in it, no other variables. So if you plug in 0, if I plug in 0, the left-hand side is 1, The right-hand side is A times 1 times 2 plus 0 plus 2 is 2 plus 0 plus 1 is 1 squared, which is 1 times 3 is 3. So you get 1 equals 2a plus 5. Subtract 5 from both sides. You get negative 4 equals 2a. Divide by 2. You get a equals negative 2. So at no point did I need to multiply everything out. At no point did I need to equate coefficients on either side. And at no point did I need to set up or solve a linear system, which I know is kind of the big headache here. Nobody likes doing that. So the Heaviside trick is wonderful. Massive time saver. Do you ever need the Heaviside trick? No. You can always do things the way I showed you last week. Do you want to use the Heaviside trick? Yes, especially in situations where you're in a time crunch, like on an exam. So it's a good thing to practice this as you solve the homework and the study guide. Now let's finish the problem. Are there any questions about how I obtained A, B, and C? Alrighty. So A was negative 2. I'm just going to record this up here. B was 1. C was 3. So now I can return to the problem I was trying to solve at the start, which is this integral. Since this function is equal to these with these numbers, the integral from 0 to 4 of x squared plus x plus 1 over x plus 1 squared times x plus 2 dx is equal to the integral from 0 to 4 of negative 2 over x plus 1 over x plus 1 squared plus 3 over x plus 2 dx. And I can split up the integral, pop out the constants, make the appropriate substitutions, and finish the job. So I get negative 2, integral 0 to 4, 1 over x plus 1 dx, plus integral 0 to 4, 1 over x plus 1 squared dx, plus 3, integral from 0 to 4, 1 over x plus 2 dx. The first two require the substitution z equals x plus 1. dz is just dx, but because these are definite integrals, I need to change the bounds. When x is equal to 0, z is equal to 1. When x is equal to 4, z is equal to 5. This guy requires a different substitution, so I'll use a different variable. W equals x plus 2. dw is dx. Again, I change the bounds. When x is equal to 0, w is equal to 2. When x is equal to 4, w is equal to 6. And implementing those substitutions, I get -2 integral 1 to 5, 1 over z dz, plus integral 1 to 5, z to the -2 dz, plus 3 times the integral from 2 to 6, 1 over w dw. And from here, things are very, very easy. This is -2 times the natural log of the absolute value of z from 1 to 5, plus the integral of z to the -2 is -z to the -1, or -1 over z from 1 to 5. And then finally here I'll have plus 3 times the natural log of the absolute value of w from 2 to 6. So this is -2 times ln 5 minus ln 1 plus -1/5 minus -1 over 1 plus 3 times ln 6 minus ln 2. The natural log of 1 is 0. And ln 6 minus ln 2, you can combine those using log rules. That's the ln of 6 over 2, which is the ln of 3. So we get, as our final answer, -2 times the natural log of 5. -1/5 plus 1 is 4/5, plus 3 times the natural log of 3. And that's it. So these problems are made much, much faster by the Heaviside trick. Even in the cases that aren't nice. Even when you have a repeated factor, the Heaviside trick will still give you some of the coefficients right away. And then when you update your equation star, you'll have something much easier to work with. Any questions on the integration step that comes after PFD? Any questions on what's on the screen right now? Any questions on the partial fractions work itself?
Can you go back to the final answer?
the next thing I'd like to do, if there aren't any questions here, is to show you how to handle the case with an irreducible quadratic factor. Since there's only one of those in your homework, I don't want to spoil that problem for you. So I'm going to grab one from the textbook instead. Before that, last call for questions on any of this problem, either the integration or the PFD. I do have a little word of caution. Please remember that the PFD is a purely algebra process. So when you start your PFD, please don't write the integral, right? Just set up your PFD, step aside from the integral, stop writing the integral, and just do the partial fractions on its own. Then come back and do the integral. In other words, solve the problem the way I solved it here. All right. So we're moving on. There's one or two examples in here that could work as an example for us. We did that one last time. Yeah, we're going to do example 5. 2x squared minus x plus 4 over x cubed plus 4x. Minus x? Yeah. So first, we're going to factor the denominator. That's always where we start with these problems. And I can factor an x there. That'll give me x times x squared plus 4. But x squared plus 4 doesn't factor over the real numbers. That is an irreducible quadratic factor. You can check a few different ways, but the easiest way is to check and see if this has any real roots. Either computing the discriminant or plugging into the quadratic formula, you'll see that the roots of this are not real numbers. They're complex numbers. It's plus and minus 2i. And while you could then factor this over the complex numbers as x minus 2i times x plus 2i, for us in the calculus sequence, we really just like to work with real numbers. So for us, this is an irreducible quadratic factor. Good news is there's no such thing as an irreducible cubic or an irreducible quartic. Every polynomial with integer coefficients can be factored into a product of simple linear factors and irreducible quadratic factors. So my PFD setup here will be 2x squared minus x plus 4 over x times x squared plus 4 equals a over x, the one term coming from the simple non-repeated linear factor, plus, remember what your PFD Bible says, if you have an irreducible quadratic factor, he gets a linear numerator. Because you have to allow for all possible proper rational functions that could have contributed to this piece being in the denominator. Since this guy is a degree 2 polynomial, the possible proper rational functions that have just him as the denominator are not just constants over him, but a linear function over him. So following the recipe from our PFD Bible, this is the setup for this function. Any questions on why this setup looks the way it does?
Why is x squared plus 4 considered irreducible?
Good question. So x squared plus 4 is irreducible because it can't be factored over the real numbers. An easy way to check is the discriminant. B squared minus 4ac. Here a is 1, 1x squared plus 0x plus 4, right? So b is 0 minus 4 times 1 times 4 is negative 16. Remember, if the discriminant of a quadratic is negative, then it doesn't have any real roots. So having a negative discriminant is equivalent to being irreducible. That's the fastest way to check. It's a good question. If you don't remember this little fact, you can always use the quadratic formula or try to find the roots of this through whatever means you remember from your algebra classes. The roots here are plus 2i and minus 2i, neither of which are real numbers. So this is irreducible.
Okay.
Cool. Yeah, I'm glad you asked. Again, from here, the first few steps look the same. We cross multiply by x times x squared plus 4. Here, the x's will cancel, and you'll get a times x squared plus 4. Here, the x squared plus 4 will cancel, and you'll get bx plus c, and it's got to be in these parentheses, because remember, fractions are like grouping symbols. We have to think of it like this. Bx plus c times x. And this is my equation star. And just like in the last problem, even though I'm not in that simplest possible case where Heaviside gives me everything right away, it will still give me some stuff. What numbers can I plug in here to make a whole chunk vanish?
0.
Yeah, if I plug in 0, this whole thing goes, right? So, following Heaviside, we let x be 0. Two times 0 squared minus 0 plus 4 is 4. A times 0 squared plus 4 is a times 4. And here we'll have b times 0 plus c all times 0, which is 0. So we get 4 equals 4a. In other words, a is 1. And unfortunately, there's nothing I can plug in that will make this go away. So from here, once I have a equals 1, again, I update. I update star with a equals 1 from Heaviside. And that gives me 2x squared minus x plus 4 equals a is 1. So this is just x squared plus 4 plus, I'll go ahead and distribute this, bx squared plus cx. And now I've got two unknowns. So plugging in something for x won't right away give me anything I can solve for b or for c, because any number I plug in that makes this go away will also make this go away, and vice versa. So from here, I do have to do the thing that we were doing last week, where you collect coefficients and set up a linear system. But that linear system will be much simpler than it would be if I had not done this. Because I already got A out, that means my linear system, instead of being a 3x3, will be a 2x2, or maybe a 2x3. Let's see. So this is equivalent to saying 2x squared minus x plus 4 is equal to, what's the coefficient of x squared? Well, I've got 1x squared here and bx squared here. So that's 1 plus b times x squared. The coefficient of x, if I collect all my like terms, is just c, so plus cx. And then the constant term, just 4. So 2 has to be equal to 1 plus b. Negative 1, right? Because that's really what this is. It's negative 1 times
Redo
x.
that. I kind of got confused.
Has to be equal to c. And of course, 4 is equal to 4. So are we comfy up to here?
Yes.
I just plugged in 1 for a and distributed this x. That gets me here. Then
where does the 1 come from?
Negative x is the same as negative 1 times x, right? That's all. So first, let me handle the right-hand side. I've got x squared plus bx squared. If you put those next to each other and factor the x squared, you get 1 plus b times x squared, right?
Yes.
So that's where this guy came from. And then cx is just cx. There are no other x's. So I'm just combining like terms. To go from here to here, I just combined all my like terms. I put my x squareds together, I put my x's together, I put my constants together. My x squareds are x squared plus bx squared. So that's 1 plus b times x squared. The cx is cx and the 4 is the 4. Are we okay with this?
Yes.
Yeah, I get it now.
Okay, cool, cool. And then over here, 2x squared is 2x squared. Negative x is the same as negative 1 times x. So I'm just writing it that way to help me see the coefficient. And 4 is 4. So now I can set the equation, I can set the coefficients of x squared equal to each other, right? 2x squared, 1 plus bx squared. Okay, then 1 plus b has to be equal to 2. Negative 1x cx. Okay, so negative 1 has to be equal to c. And then constants have to equal each other. So 4 is equal to 4. That's not super exciting, but it is nevertheless true. Now this linear system, I think you'll agree, is a shitload easier than the 3x3 we had to mess with on Friday. Right away, it tells me that c is negative 1, and this equation only involves b and constants. So here, I can subtract 1 from both sides, and I get 2 minus 1 equals b. That's 1 equals b. And right here, I've got negative 1 equals c. So that's it. Now I've got A, B, and C. I got A from Heaviside, and then I had to fall back on the methods of last week to get B and C. That's because of the irreducible quadratic factor. So if you have a repeated factor or an irreducible quadratic factor, Heaviside won't get you everything. But it will still make your life easier. Now I can go back and do my integral. I know that A is 1. I know that B is 1 and that C is negative 1. So according to my PFD, the integral of 2x squared minus x plus 4 over x times x squared plus 4 dx is equal to the integral of 1 over x plus 1x minus 1 over x squared plus 4 dx. And this integral I'm going to split into 3 pieces. This is the integral of 1 over x dx plus the integral of x over x squared plus 4 dx minus the integral of 1 over x squared plus 4 dx. So I did 2 things in this line. I split this fraction up as x over x squared plus 4 minus 1 over x squared plus 4. Remember, you can always split fractions up across their numerator like that. Can't do it with denominators, but you can do it over numerators. And I also gave the integral to each of the 3 resulting pieces. This first guy is utterly trivial. This second guy requires a substitution. Z equals x squared plus 4. dz is 2x. This guy also requires a substitution, but what kind of substitution?
Trig sub?
Good, very good. This is a tangent substitution. The x squared plus 4 tells me to substitute x equals 2 tan theta. And dx then is 2 secant squared theta d theta. So I'm going to take the middle integral and the far right integral and handle them separately. I don't want to have to keep writing every little thing. So here, this guy is going to become 1/2 integral 1 over z dz, which is then 1/2 natural log z, which is 1/2 natural log x squared plus 4. I could get away with the simple u sub here because I had an x upstairs and the derivative of the bottom is 2x. Over here, the integral of 1 over x squared plus 4 will become 2 secant squared theta d theta, that's the differential, over 2 tan theta all squared plus 4, which is integral 2 secant squared theta over 4 tan squared theta plus 4 d theta, which is integral 2 secant squared theta over 4 times tan squared theta plus 1. You factor the 4. And then tan squared theta plus 1, that is secant squared. So I can pop the constants out, 2 over 4, that's 1/2 integral secant squared theta over secant squared theta d theta. These cancel. And you get 1/2 integral of 1 d theta, which is 1/2 theta plus c. And then theta, remember, if x is 2 tangent theta, then x over 2 is tangent theta. So theta itself is the inverse tangent of x over 2. So I get 1/2 inverse tangent x over 2. plus c from him. This guy over here, he was done. Nothing to do. So all together, we get natural log absolute value of x plus 1/2 natural log absolute value x squared plus 4 minus 1/2 inverse tangent of x over 2 plus a constant. And that's it. This is how you solve all of these PFD problems. The sort of worst case scenario is something that requires trig sub, and it'll always be a tangent sub because the irreducible quadratics, they're not always like x squared plus a constant, but you can always complete the square in the worst case scenario and get something that looks like u squared plus a squared, which means that it's worth doing something here. It's worth proving this formula because you don't want to have to write all this stuff down every time you see an integral that looks like this. I don't want you to memorize this. I want you to prove it. I want you to solve this integral in general. So for any constant a, find the value of the integral 1 over x squared plus a squared. It will come out to this. So you know what to shoot for. And it comes from this sort of substitution. You would make the substitution here in general, x equals a times the tangent of theta. Dx is a secant squared theta d theta. It's not a hard problem. And it's one of those integrals that I recommend having readily available. But that's it, lads and ladies. That is the Heaviside trick to speed up your partial fractions problems. And that's how it looks in all of the possible cases. The only thing we haven't addressed directly through an example is what you do if you have a repeated irreducible quadratic. But it's the same bullshit. There's no difference between this and that. So you use Heaviside to get everything you can. Get as much as you can with Heaviside. If you have an irreducible quadratic factor or a repeated factor, Heaviside won't give you everything, but it will still give you some good stuff. Take that good stuff, update the equation star, and then fall back on the methods that we learned last week, which are the general methods, the methods that always work. But use Heaviside. Use Heaviside as often as you can because it will save you a lot of time. If you want to see a little further discussion on this, let me see if I still have it. No, okay, so I will dig it up here. So you can watch an MIT TA go through some of these problems, but the real thing I'm looking for is this, yeah. So there's a PDF here that justifies the Heaviside procedure. And it shows you why this works and in general how things go. So I'll link this in a module. And you can take a look at that for a little bit of extra stuff. But mostly what I encourage you to do is first and foremost, finish the homework. Then finish the study guide. If you want more practice, having done both of those things, then you can look at the textbook. Section 7.5 doesn't actually have any new content. What it does have is an amalgamation of problems from all of the previous sections and this nice table of integrals that you gotta know. certainly all the way up through 18 here. You should know all of these cold. You'll notice number 17 is the formula I asked you to prove. The rest of these are foundational basic integrals that hopefully everybody already knows, but if you don't, beat them into your head. 19 and 20, I wouldn't necessarily recommend memorizing. They're a little bit more complicated and they're not really worth the space in your brain. We don't see them as much and they're not hard to cook up as needed. But for more practice, read through section 7.5. We're going to do this together on Wednesday because this is a really good review for the exam. But then, if you've done all the homework and you've done all the study guide problems, go in here and start attacking these. Solve every single one. If you can solve all these problems, you are going to nail the test, I promise you. Any questions for me before we sign out for the day? All right, so congratulations. You guys now know how to integrate as well as anybody else on the universe, on the planet. In theory, you now know all the standard tricks. What I've shown you, that's it. Integration is fucking hard. There's lots of integrals. You go writing down random integrals, the odds are there's no nice way to solve that problem. But all of the tricks that anybody knows, you now know. So you've got all the integration theory that you need to be a rock star engineer or to begin graduate school in mathematics, all that stuff. We are going to talk about very different things after exam 1. Okay, I'm going to do my best to introduce them gently. We're going to talk about certain special kind of integrals that will help you understand the concept of the word convergence. And then we're going to start talking about sequences and series. And that is, for most people, the most intimidating part of this course. So prepare well for exam 1. Exam 1, you want it to go well. It's not terribly hard, but you do need to practice. So make your first priority solving all the homework problems. Actually really solving them on your own. No Symbolab, no Bartleby, no bullshit. Then do the same thing with the study guide. And remember, you need to write out your solutions to the study guide, scan them, and submit them in Canvas. That is where the study guide grade comes from. The study guide grade does not come from the WebAssign completion. It comes from you scanning and submitting your work. I don't care if everything is perfect. It doesn't need to be perfect. It's not graded for correctness. It's just graded for completeness. And it gives me the opportunity to give you some written feedback before the test. So please get the study guide done, scanned, and submitted as soon as you can. That way I can get you some feedback that you can review before the test. Once you've done all of that, if you still would like to prepare more for the exam, go to section 7.5 and just start solving problems. If you can solve all the problems in section 7.5, you will do great on this test. Remember, there is going to be some volume stuff and some area stuff on the test. So you need to remember the geometry as well. Wednesday, we're going to review. Friday, there is no class because Santa Fe's calendar committee has their head up their ass. And then Monday is going to be the exam. If you look under your Canvas announcements, you'll see an announcement explaining exactly how I want you to complete and turn in Study Guide 1. I'll post a very similar announcement for Exam 1, explaining the exact procedures. Please read both of those in their entirety to make sure that you do things correctly on the day of the test. The test, again, is next Monday, 1 week from today, October 5th. If you have any questions, you want to talk more, solve problems together, any of that stuff, come see me in office hours. I have my regular office hour this afternoon. Otherwise, I will see you guys on Wednesday. All right.
Have a good day.
All right, guys, have a lovely rest of your day, and I'll see you either later today or on Wednesday.